Welcome back. This video is part 3 as we continue to work through section 4.1 of the text. We've been talking about scatter diagrams, and we introduced in the last video, we introduced the notion of the linear correlation coefficient. And so we've been talking about the properties of the linear correlation coefficient. We'll wrap that up now, and then we'll talk about computing and interpreting the linear correlation coefficient. So here's another example. We have bivariate data. We have an x and a y. And we notice here that as x increases, y is increasing. And the thing you notice in this example is that the relationship between x and y forms a perfect straight line. So this is going to be the exceptional and unusual case where our correlation coefficient, r, will turn out to be precisely 1. Indicating a perfect positive linear relation between x and y. Here's another example. The same type of thing. We have as x increases, y is decreasing, but now it's decreasing in a perfect linear straight line. So our correlation coefficient here, if we were to calculate it, is going to turn out to be precisely -1. And we can talk about one more property of the correlation coefficient, and that is that we say the correlation coefficient is not resistant. Now what that means, if you recall, a statistic is resistant if one or two extreme or unusual values don't affect its value substantially. But what we're saying is that's not the case with the correlation coefficient. The correlation coefficient is sensitive to a few extreme values. Let's look at an example of that. So here's another small data set. I've got an x and a y variable. We can look at the scatter plot and we can look at the correlation coefficient and say that, well, there's a very strong negative linear relation between x and y. The correlation coefficient is essentially -0.99, almost -1. So it is an extremely strong negative linear relation between x and y. But now what I'm going to do is I'm going to take this point right here, the point where x has a value of 2 and its y value is just under 15, and I'm just going to change that data point. I'm going to change that point in the data, and I'm going to put it here. So now I've got x equals 2, y equals 0. So again, I'll go back here. This was my original point. And I left all the other points in the data the same, but I just changed this one point from having a y value of just under 15 to having a y value of 0. And now you notice what happens to the value of the correlation coefficient. It goes from, originally it was essentially -0.99, and by changing that one data point, leaving all the rest the same, the correlation coefficient goes to -0.69. Pretty substantial difference, and that's a result of simply changing this one data point. So that's what we mean when we say that the correlation coefficient is not resistant. One or two extreme values in our data can really have a substantial impact on the value of the correlation coefficient. Now this slide is a summary of all the properties that we've been discussing, the properties of the Pearson linear correlation coefficient. And this is a slide taken right out of your book. This is from page 196. And so as you go through your textbook and you're reading this section, you want to go through these properties carefully and just make sure that they all make sense to you. So here are a few more examples to illustrate what we mean when we talk about the value of the linear correlation coefficient. Example A up here, this should look familiar. We just looked at something like this. In example A, we've got a perfect positive linear relation between x and y. As x increases, y increases, and the observations all fall perfectly on a straight line. So our correlation coefficient turns out to be exactly 1. Now, as we said, this is not the way things usually turn out in practice. In practice, we'll usually have something more like example B or example C. In example B, as x increases, y tends to increase as well, tends to increase in a straight line manner, but there's some wobble in the values of y. So if we were to calculate the correlation coefficient here, we'd probably get something like r is approximately 0.9, indicating a strong positive linear relation between x and y. If we look at slide C, we still have a positive linear relation, but it's more of a moderate relation because as x increases, y is tending to increase, but there's quite a lot of wobble in the values of y. So here we might see a correlation coefficient of something like 0.4. In slide D, we see this perfect negative linear relation again. So we would compute a correlation coefficient of -1. In slide E, we have a negative relation between x and y. As x increases, y is tending to decrease, and it's a pretty strong negative linear relation. Here we get a correlation coefficient something like -0.9. In example F, we've still got a negative linear relation, but it's not quite as strong. We might calculate an R of something like -0.4 here. And if we look at example G, you notice what happens as x increases, y is just all over the place. There's no systematic increase or decrease in y as x increases. So what we would find here is our R correlation coefficient would end up being close to 0, and we'd conclude there's no linear relation between x and y. And in example H, now this is a little bit of a different kind of situation. If we look at what's happening to our values of y as x increases, it's pretty clear that there is a strong relationship here between x and y. As x is increasing, the y values are tending to increase for a while till they reach a peak, and then they begin decreasing again. So there's a pretty clear and strong relationship here between x and y. However, notice it's not a straight line relationship. It's not a linear relationship. So if we had the data for this example, and we were to calculate the correlation coefficient, even though there's a very strong relationship between x and y, because it's not a linear relationship, we would compute our correlation coefficient R, and it would come out to be close to 0, indicating, again, no linear relation between x and y in this graph. Now, let's talk a bit about computing the correlation coefficient. We had this slide in the previous video, and we said that this is the formula for computing the value of the correlation coefficient. It's a somewhat messy looking formula, and as I said, we're not going to ask you to calculate this by hand. We're going to let the computer calculate the value of R whenever we've got a data set in front of us. And so we're going to use either StatCrunch or Minitab to do our calculations for us. So now let's take a look at a real data set so we can calculate the correlation coefficient. Now, if you recall, this is a data set that we were looking at in a previous video. This is from problem number 25 on page 204 of your Sullivan text. And the data set contains data on 11 automobiles. Now, on each automobile, we've got its weight and its miles per gallon. So again, this is what we call bivariate data. We've got two variables on each observation in our data set. Now, what we're going to want to do is calculate the correlation coefficient between weight and miles per gallon. Now this data set is available in Minitab, and it's also available as a StatCrunch data set. And if you recall, in one of our previous videos, we pulled this data up in Minitab, and we created the scatter plot you see right here. We've got two variables, weight and miles per gallon. Each dot represents an automobile. Of course, as weight increases, our miles per gallon tends to decrease. Now we would say that our miles per gallon tends to decrease linearly as weight increases. So we could say that there appears to be a negative linear relation between weight and miles per gallon. And if we compute the correlation coefficient for these two variables, we would expect its value to be negative. So now would be a good time to put this video on pause and go out and take a look at the videos we have available for how to compute the correlation coefficient in Minitab and in StatCrunch. We have separate videos, one for each software. So you're going to want to take a look at those videos and then pull this data up in StatCrunch or in Minitab and compute the correlation coefficient. What you should get is this. Just as we expected, our correlation coefficient for these two variables should turn out to be minus 0.964, a very strong negative correlation.